Please allow me to introduce our next speaker, Rogier Windhorst. Rogier received his PhD in astronomy from the University of Leiden in the Netherlands. He completed his postdoctoral work at Carnegie Observatories and Caltech in Pasadena, California. Windhorst is a Regents and Foundation Professor at Arizona State University and one of the world's 6 interdisciplinary scientists for the James Webb Space Telescope. Please join me as we listen to Dr. Windhorst.
So we're going to talk about the world of Webb, the cosmic circle of life, and seeing through the eyes of Einstein. The Webb telescope is an infrared telescope, as you heard David Block and Jeff Swering talk about. It's also far away from the Earth and the Moon to get us a completely dark spot in space behind the sun shield. And that spot provides a sky background that is between 10 and 100,000 times darker than what you get from the ground in the near infrared. Stated differently, Hubble has a little bit of that advantage too, and it acts as a 64-meter telescope on the ground with that same sensitivity in space as a 2.4-meter telescope. Not the same resolution, but the same sensitivity. You'd need a telescope a couple of 100 meters in diameter on the ground to beat what Webb is doing in space, and that is because the sky is so dark. So I've asked the organizers, therefore, when the pretty images come along, to turn all the lights off. Please don't trip in the dark, but you will enjoy it better when you're dark adapted. Yeah, so these first 3 points, as I said, is what we're going to talk about. Then I'm going to run out of time. I don't want to follow the example of the telescope. It run over time and budget many times. I won't do that today. But I have a whole bunch of spare charts for the discussion, and I already heard a couple of questions that we probably want to talk about a bit more in the discussion session. So I'll start out saying personally, when I had just gotten to Arizona State in 1987, Pope John Paul II came to give a mass. He gave a mass in Sun Devil Stadium. The first thing he said, it was hard for him to be in Sun Devil Stadium. Unbeknownst to me, this would be lead to my lifelong mission with Hubble and Webb, and also having a mission from the Lord here. And I'll tell you how this came about. It's as if the Lord himself will establish a house for you. What happened is he gave $10 million to Peter Strittmatter over lunch that day to build the Vatican Advanced Technology Telescope on Mount Graham. And as luck would have it, or as God would have it, we were the first to use it 9 years later in 1996 in October. And we made an image of nearby galaxies, the beautiful grand design spiral structure you have seen. We put a text in there and I'm not even Roman Catholic, right? But in Latin that says the beauty of nature in ultraviolet light, and that was a precursor of what Hubble would do at higher redshifts. You want to look at local galaxies in the UV to see the same kind of stars. We gave a copy to the Holy Father during a conference at the Vatican in November '96, and then received this beautiful thank you note from Pope John Paul II a month later, written in Italian with the papal blessings. So that was totally unexpected. Anyway, a warning for the talk is asking NASA for Hubble images is like drinking or taking a sip from a fire hydrant, but asking NASA for Webb images is like taking a sip from the Niagara Falls. So I suggest children don't do this at home, and bear with me if I go a little fast, because I have a lot of good images. I'll keep it mostly to the images and relatively little text. So we were launched on Christmas Day 2.5 years ago, one of the greatest Christmas presents ever, and it was a picture-perfect launch. I had hammered hard during the 24 years that I was on the Webb team with NASA to make sure that they would launch with a full tank of propellant, and they did. And then the French gave us a perfect launch, perfect orbit. So instead of 5 years requirement and 10 years goal, We now have propellant for 27 years. It's kind of like, doctor telling you, well, you won't die of this, but you'll die of something else. Probably some other parts will fail before we run out of gas, right? But if we have our gyros and batteries last for 15 years, then I'll call it a day. If we last longer than that, like the Hubble Space Telescope, so much better. But in any case, we're doing good. So this was the telescope, a selfie taken, not a selfie actually, it was taken from the Ariane upper stage over Saudi Arabia and the Gulf of Aden. And here then is the first selfie of the telescope a few months in after it had deployed the mirrors. And you saw 18 out of focus stellar images to the right because all 18 panels were not properly aligned in all 7 free parameters that we had. So it took them a few months to tinker with that. This was planned, of course. And then in March, they had 18 in-focus images that they then tilted the mirrors and stacked them all on top of each other. And that gave us, for the first time, a working telescope. So my good friends who took this image in March of 22, they obviously looked at this beautiful focus star. This would be a good time to turn all the lights off. Let there be dark. Yeah, thank you. For this better viewing of with your eyes, if you can. And so you see all these background galaxies behind this star, and the guys who were observing this were all exoplanet observers, but they were more excited about about the galaxies in the background than the focus star itself. So here you see all 7 panels. Well, there is 2 cameras and 2 spectrographs. The near-infrared camera made by Marcia Ricci at the U of A at the top, the Canadian fine guiding sensor that holds the telescope still during long exposures, also backs up as a spectrograph, which is that nearest thing to the lower right. Then the European NIRSPEC spectrograph that does many objects at once. And then also a European component called the mid-infrared imager that takes images at longer wavelengths. This is a family portrait of just a region in the Large Magellanic Cloud, 160,000 light years away. And you can see here in an enlargement to the left the Spitzer image, the old 85 centimeter infrared telescope at 8 microns, and to the right the Webb image. The Webb image is substantially deeper and sharper, of course. So before we get to the cosmic circle of life, a warning that what you learned in high school about the periodic system is not actually fully correct. We will see the hydrogen and helium, the blue tiles, and a little bit of lithium, as Jeff and you pointed out, is made during the Big Bang element production. Then dying low-mass stars like the sun will deposit the things in the middle in green, and merging neutron stars will deposit at the end of their lifetimes when they merge the elements in purple, which is pretty much the bottom 2 or 3 rows of the periodic system, including the radioactive elements. And then everything in brown in the lower right is made in only in the Earth-based laboratory. And exploding massive stars make the yellow elements, and exploding white dwarfs, the type 1a supernovae that you'll hear more about, make the 3rd row, including iron and nickel. So I hope you had your calcium, magnesium, and zinc for breakfast this morning, but it was all made in stars. This is important because only hydrogen, helium, as you heard today, were made in the Big Bang. Everything else is made in stars. So you're literally made out of stardust. This is the correct periodic system. Yeah, 76% hydrogen, 24% helium, and then some of the hydrogen gets converted inside stars to helium and then into the heavier elements. So the cosmic circle of life will consist of seeing where these heavy elements are produced inside stars and how they then make it out of stars into planetary systems, one of which we're lucky enough to live on as the Lord has given us. And so we people and planets are literally made out of this stardust, the heavier elements in the periodic system. One of my Christian friends gave me this verse in Jeremiah 33:25. The Lord established his covenant with day and night and the fixed laws of heaven and earth. I want to point out that this periodic system, these proportions, are the same everywhere in the universe, yeah? No exceptions. You may have a little more or a little less, but you have the same ratio of carbon to nitrogen to oxygen to hydrogen everywhere. That is because, in the previous graph, these proportions were made inside stars. Stars form out of these giant dust clouds, as you already saw in David's talk. The left image was the one made at ASU by Professor Jeff Hester and Paul Scowen with the Hubble Wide Field Camera 2. These three giant columns, light years across, of cosmic dust, which are being shown upon by stars that are a little bit above the image. They sculpt this gas into pockets and fingers in which later on, I will try to show that here, at the end of these fingers over here with the cursor is where stars like the sun are forming. And if you look at an enlargement of this, you can see, this is now further into the mid-infrared, that at the end of these fingers, here's one and there's one, with the stars to the upper right, not shown in this image, shining down with their ultraviolet radiation, sculpting these clouds. It is in the aftermath of these bright stars that these low-mass stars like the sun are forming. A better version of that is probably the cosmic cliffs, or this Tarantula Nebula seen in the Large Magellanic Cloud, where there is a giant star cluster here, the blue pile of stars to the middle of that dark Christmas tree. And again, there is an enormous cavity of dust and gas being evacuated by the ultraviolet light and the supernova explosions from these bright stars. So we call this the cradle of cosmic star formation. It's the massive stars that trigger the formation of sun-like stars. I sometimes liken them to the cosmic fraternity members. They live fast and die young. You know, massive stars live 2-3 million years, then they go boom. If you heard, as you heard in Yu's talk, and it's in the aftermath of those stars that stars like the sun, have been forming. The cosmic cliffs you have already seen. I think of this as a cosmic beachhead, where the brown material is the gas and the dust left over from previous generations. And on the top are all these bright stars with the blue, not the ocean, of course, the ocean of ultraviolet light, shining down on this beachhead and shaping it. And indeed, you can see that in the various pockets of this beachhead, there and there are stars like the sun are forming. I will take a quote from Hugh Ross here. I hope I say it right. But God has given a name to every star in the universe, about 10 to the 23 stars, Avogadro's number, if you want to remember that correctly. That would be approximately 1 trillion stars for every human, as you quotes it, that has ever lived to name. That would be, you all need to be naming stars at the rate of 1 per millisecond, please, so we can name all the stars in the universe. Yeah, that's a lot of stars. Anyway, and they get formed in groups and clusters simply because this material is so dense and they come seldomly alone. We, as the sun, are lucky that we're not part of a double star. So this is in the Carina Nebula, and it's called the cradle of cosmic star formation. At least that's what I call it. I should say, by the way, my wife asked me yesterday to say that, that at home, because of all the many trips that in the last 40 years that I made for both Hubble and Webb to Baltimore, and she's suffering from that. At home, we don't call this telescope the James Webb Space Telescope. I call it the JWST Windhorst Space Telescope. It does have the same acronym. Okay, so here's the Orion Nebula. You've all seen the trapezium that is not actually shown here, but another cosmic cliff, if you wish, where bright stars are shining down on that dust and shaping it. And here in the lower right is a protostellar nebula already forming with molecularly, the MIRI instrument has shown that there's a carbon chain in there called methylcation, if I say it correctly. This is 1,300 light years away from Earth in the Orion constellation. David showed this one, so I'll go through that quickly. This star is only 30% of the mass of the sun. It's in the very center of this hourglass-shaped mass. It's only 100,000 years old. So in the middle here, you can imagine there's a protoplanetary disk already rotating. The sun is just beginning to shine and illuminate the surrounding gas, both north and south. and eventually it will shine like a full star with all the gas blown away, and that happens more rapidly than you think. Here's another region where that happens in the Ophiuchus constellation, with a couple of stars like the Sun forming there. This is only 456 light years away from us, and this particular one is already showing chemical elements like polycyclic aromatic hydrocarbons. So those are, organic elements, not life, but building blocks of organic elements that also make it onto Earth. David showed this one, so I'll go through that quickly. That's 1400 light years away. This protoplanetary disk, it's actually a double star at the location of that orange asterisk in the center. That's squirting out these two jets in opposite direction from the fast rotating protoplanetary disk. It's a messy process. A lot of material falls in and a good bit gets thrown out as well. If all goes well, you get a nice star in the center, such as this star Fomalhaut that you're all familiar with, because you can see it with the unaided eye in the winter sky. And it has in the infrared a beautiful debris disk surrounding it. And in these ringlets, the star itself here is suppressed with a cold finger at the location of the black dot. You can see these orange ringlets is where planets like Jupiter and Saturn will be forming. And indeed, you can see already here that this is happening at the mid-infrared wavelengths. So this is how giant planets and terrestrial planets also will have formed around our sun. Yeah, not unlike this example here, but in different proportions, of course. You have already seen this one today. Again, a cold finger is holding the starlight down, and you can see a disk that is about the size of a little bit bigger than Pluto's orbit, 60 astronomical units in radius. So that's a protoplanetary system at the two main infrared wavelengths, and we see it edge on here. So it's, again, a messy process. This one is by no means done yet. Jeff has shown this one already. It's 10 Jupiter masses, 15 megayears young, so it's, one of these stars with a phone number. The star itself is suppressed again with a cold finger or coronagraph at the location of the asterisk. And the planet, while a little deformed in the optical image, is clearly seen at all 4 mid-infrared wavelengths. And it's a rather cool planet. I'll show you one or two more spectra. This one, wavelength running from the visual to the left to the near-infrared, 3 microns to the right. Intensity vertical, and you can see various water features are clearly visible. The blue line is the model, the dots are the data. The only problem is that this is not really water, it is steam, because this planet is 1,000 Fahrenheit in temperature and half a Jupiter mass. So it's not a place I would want to live, but it is a planet with water. And we hope, of course, that Webb will discover many more of these planets and also Earth mass-like or maybe super Earth mass-like with real ocean-like water. We haven't gotten there yet. So at the end of the lifetime of a star like the Sun, it will throw out its outer layers, and that is courtesy of the fact that the Big Bang lasted just short enough to produce no more than 24% of helium. If it produced 100% helium, which it could have, or even carbon, nitrogen, oxygen, then the outer layers of these stars would have not been thrown off so easily. It is the initial hydrogen burning in the center that then propagates outwards, and then helium burning in the center that propagates outwards, and then it stops. And in the case of the Sun, it stops because we're running out of elements to the nuclear fuse, and therefore the outer layers will get slowly thrown out. This will happen to our Sun in about 5 billion years, and all the heavier elements that are produced inside our star, like the ones in the bottom of the periodic system, most of them, not all of them, will get thrown out and be part of the cosmic circle of life. Out of that gas and dust you see here, new planets will form. So I couldn't resist showing the important Bible verse that captures this well. For dust thou art, and unto dust shalt thou return. This is not only true for people, it is also true for planets and stars. Yeah. And that is important to keep that in mind. Here's the same picture again in the infrared. And thanks to all this dust that is being expelled, new stars will form with planets in the future here. Let's see how we're doing time-wise. This is probably one of the most beautiful ones. You can see this one with a small telescope in the northern sky in the constellation of Lyra. The Northern Ring Nebula to the left is the near-infrared image. To the right is the mid-infrared image. And I believe, and I have to stare myself really hard, the very star in the center, which is now a white dwarf, has already shed out its outer layers here, as you could see also in the previous images. And this is what the sun will do in about 5 billion years. Again, it is part of the cosmic circle of life. We form out of dust and we deposit the dust back into the interstellar medium later. And in all cases of low-mass stars, a white dwarf is left in the center. If a star like this were heavier, it wouldn't get to this stage. Instead, it would rapidly start burning the heavier elements like carbon, nitrogen, oxygen, and silicon, and eventually iron. And then iron cannot fuse any further. It produces no nuclear energy to go up to higher elements, and therefore the star then collapses and becomes a supernova, and the center becomes a black hole or a neutron star. That doesn't happen for stars like the sun. Here is a massive star called Wolf-Rayet, and then some phone number before it turns supernova. It has already shed out its outer layers, and the star is still visible in the center. And probably in a few 10 or 100,000 years, it will actually explode as a supernova, both seen in the near and mid-infrared. This process will also release a lot of dusty mass. So again, Genesis 3 verse 19 in action. And then last but not least, the supernova 197A that you could see in the Large Magellanic Cloud. I was Carnegie Fellow down the road here. And in Chile, folks had seen this star explode right at that time. I think it was in February of '87. And over the decades, these new shells of material have been illuminated by the material that shocked into it from the supernova explosion, and that causes these beautiful hourglass-shaped nebula, basically the aftermath of a supernova. These supernovae are pretty rare, but they do happen. This is the Cassiopeia supernova in our own galaxy at the mid-infrared wavelengths. And you can see here all the cosmic dust made out of the carbon, nitrogen, oxygen, silicon components in the interstellar medium, primarily rendered in the yellow and green and some red colors. I don't remember which color indicates which molecule, but we can look that up on their website. But this happened in our own galactic neighborhood. These are rare. In our own galaxy, supernovae do not go off more often than once every few centuries. Not that we see. They could be hidden by the dust. In other galaxies, as we'll see, it happens much more rapidly. Here's another galaxy, M83, a nearby spiral. The top is the near-infrared image. You can see the red spiral arms is where the hydrogen is being glowed up by the blue stars that have just formed. Most of that illuminated gas is in the outskirts following the spiral arms, and in the mid-infrared where you see the molecular structures, it follows the same spiral pattern but with a lot more fine structure, and this indicates the areas where stars like the sun as well as massive stars have been throwing out their dust. So again, through dust thou art made, stars, and dust shalt thou return, stars. This happens also in nearby galaxies. In fact, it happens in every galaxy we look at. They have this beautiful dust pattern that stars are being made out of and that are returning their dust at the end of their lifetime. So this is the end of the cosmic circle of life that rules throughout the universe. Then the second part of the talk is looking through the eyes of Einstein. So Einstein made a lot of predictions, many of which he actually doubted or not liked. He didn't like the prediction of black holes at all. He didn't like the Hubble expansion prediction because he put in this cosmological constant to make the expansion go away for a little while, at least anyway. And then when his friend asked him to make a prediction about gravitational lensing, Einstein, you said that gravity curves the light. What does that mean? Does light go around a star and can you actually see it have been displaced? And this is what made Einstein famous when Eddington discovered this during a solar eclipse in 1919. But his colleague asked him to predict what would happen if a galaxy was lensing the light. And Einstein made the prediction and said, yeah, it will happen, but it's such a small effect you can never observe it. Well, we'll see that you can actually observe it, and Einstein was right in everything he predicted. This is what we call Stephan's quintet. It's 40 million light years away, 4 colliding galaxies. The spiral there at 10 o'clock is in the foreground, and this is a cosmic train wreck. These cosmic train wrecks are much more common in the past than they are today, and sun-like stars will form in the aftermath of these minor mergers or cosmic fender benders. This is not a giant train wreck yet. We will see some train wrecks in a minute. This is what it looks like in the mid-infrared. The same 5 galaxies with the blue spiral in the foreground off there to the side. And the galaxy at the top at 12 o'clock has a very bright star in the center. That ain't no star. That is a supermassive black hole with a giant accretion disk that shines through the dust just fine and produces this red star-like pattern. And this is common. As you heard earlier today, many galaxies have a supermassive black hole in the center. This is more a rule than an exception, and I will show you some more pretty pictures, including this one, and including some more galaxies that have the accretion disk of a supermassive black hole in the center. This one at 24 million light years clearly has a star-like feature in the center. So these were the very objects that you, Ross, was looking for in this dissertation. They're there everywhere you look, almost. Sometimes they're tiny black holes that are feeding a little bit. Most of the time they're supermassive black holes and they eat like a beast. Yeah, and in many cases they will outshine the galaxy. You can't even see the galaxy anymore. At this resolution and this relatively low redshift, you can see the galaxy just fine. But you do need the infrared for that. Here's another example that looks more like a quasar. In fact, if you put this one at the distances that you was looking at, then you would not see the galaxy so much anymore. You just see the quasar in the center, 220 million light years. It does have a supermassive black hole, and it's feasting on the infalling gas. That's why the accretion disk got so bright before it falls into the Schwarzschild radius. It really heats up to X-ray temperatures, and it shows off in the ultraviolet as well. And then, of course, also in the optical and redshifted in the infrared. The surrounding area, gas is expelled at very high speeds before it falls into the black hole, and it can form relativistic jets or just, bipolar outflows that look like these huge hourglass-shaped cones of gas that is being pushed out. Here's some of our own work leading into more of Einstein's gravitational lensing. We just decided to observe for fun, not just deep fields and gravitationally lensing fields, but also an overlapping galaxy. My colleague Bill Keel came up with this idea, said, Roger, let's look at the spiral that's being, by accident, back illuminated by an elliptical galaxy that's almost, not quite at the same redshift. So you can actually see the spiral arms there close to my cursor from the spiral go in front of the elliptical. And since the elliptical is rather regular in its light distribution, you can actually map the properties of the dust. It turns out this galaxy has smaller dust grains in the outskirts than our galaxy does. And one of my students found another 150 globular clusters in this elliptical galaxy. And if you enlarge it a bit, you can also see there was a gravitational lensed object behind the elliptical. Turns out to be galaxy redshift 1 that was turned into a nice arclet because of the gravity from the ellipse itself. I think David showed you the cartoon how that happens. There was even a counter image here of that gravitational lens over there, and that happens often. How we're doing at time? Somebody fill me in. Yeah, I got to tell you the story. We call this the Biden image. It was the image that President Biden released a day early on July 11, 2022. One of my team members then co-selected this beautiful lensing cluster, which happens to be at a distance of 4.5 billion light years. And one of my other team members, Anton Kokomor from South Africa, drizzled the image. And then he showed it off. They showed it off to their director at the Space Telescope Science Institute in Baltimore. And she fell off her chair, and she sends it up to Goddard Space Flight Center, where the project manager fell off his chair, and he sends it up to NASA headquarters, where eventually the NASA administrator fell off his chair, and then they sent it up to the OMB, where the science advisor of the president fell off his chair, and they sent it up to the White House, straight to the Oval Office, and Biden says, no, I'm going to release this myself a day early. So there it is. We were going to release all the images on July 12th, but the president released this one a day early. Fortunately, he got called out of the meeting pretty quickly, so he didn't scoop us on our Nature paper. But anyway, the important message is here that these galaxies are already, these cluster galaxies, these white things at 4.5 billion light years distance, are already 9 billion years old. They were formed at redshift 10 or 12. And they are therefore already grown into very massive objects that distort all these background galaxies into these beautiful lensing arcs. This, by the way, is the Hubble image, which was 10 times longer than the Webb image. So you can see that Webb made a big step forward in terms of sensitivity and contrast and everything. The important message I have for you here, that the cluster itself, this lensing cluster SMACS 0723, is 3 times older than the Earth today. We're cosmic late bloomers, if you wish. We're the cosmic late kids on the block. And I'll argue that this is a good thing. This is how God designed it. It's good that we formed in a star that didn't form early, because first of all, it wouldn't have had all the chemical elements, that as you heard in Hugh's talk, that we need today. And secondly, the universe was rather violent, as you will see, a redshift of 1. And I'm very happy that we were only born in a redshift 0.4 or 0.5. So here's another cluster that images a object, a double galaxy at 0.4 billion years, which is a redshift 10, so 400 million years after the Big Bang. You see an image there in this box, in that box, and that box. The galaxy is actually right here behind this cluster, but because of the bending of the light that Einstein predicted, you see the yellowish and the reddish companion 3 times under 3 different angles. It is the same galaxy, and this then allows you to map it in detail at great contrast and fantastic resolution. By my colleague Dan Cohen, his student at Johns Hopkins. Another one of the team members found this cluster, and this showed a beautifully lensed gravitational arc, where you need to understand that when Einstein predicts that this lensing happens, these always come in symmetric pieces. So here's an object behind this cluster component that gets cast over here and there, and there's another galaxy part that gets cast over here and there, but then there's one star right in the center on what we call the critical curve, where in the gravitationally lensed source plane you can get nearly infinite magnification. You heard Ross say that, you know, you want to have a 5 sigma detection if you want to believe something. Well, this star was originally 0.001 sigma in its flux, but because the magnification is 9,000 times, we can see the star at 4 or 5 sigma just fine, right? And it's because of the gravitational magnification that we can see it. So it's only because the magnification from this gravitational landscape is so significant. I couldn't resist putting in Proverbs 3 verse 6, in all your ways acknowledge him, and he will make your paths straight. That is straight in 4-dimensional space-time, right? It's really a curved path, as it should be. But your paths better be straight. But in relativity, they can be curved. Here's another example. This cluster, selected by my coworker Brenda Fry at U of A, G165, it's the brightest far-infrared source selected by the Planck satellite in the sky, redshift 0.35, so it's 3 some billion years in the past. Not that far. It's one of the more massive clusters. It contains about 10 to the 15 solar masses. So this set of 3 galaxies here and 3 galaxies here, 10 to the 15 solar masses worth of stars in total. That's roughly about as many stars as there is pennies in the national debt. Yeah, it's a big number. That's not the point here. The point here is these 2 orange worms. These 2 orange worms are 2 highly distorted galaxies imaged several times because of the tremendous gravitational distortion from these foreground cluster galaxies. And they're at redshift 1.78 for this string over here, and redshift 2.3 for the other string over here. So they're seen, 3 or 4 billion years after the Big Bang. And in the right panel, you can see that the worm to the left has not only a galaxy center that gets shown 3 times, so there's 3 different light paths where you observe it, but there's also a point-like object that appears at 3 different locations away from that lensed galaxy bulge. And that is a supernova 1a at a redshift 1.78. So that is seen 3.6 billion years after the Big Bang. And because there is 3 different light paths that give you those 3 images, and we observed it also 3 times, we asked the director immediately after this discovery a year ago to get 2 more epochs, and she gave it to us. And so we now have 9 images of this supernova. We know it's a type 1a, and we have a measure for the Hubble constant at that redshift. By the way, this is a perfect location to keep doing this observation, because unlike our galaxy that produces a supernova every few centuries, we predict that with 350 solar masses a year, there will be at least 1 supernova per year going off in the observed frame for the observer if we continue looking at it every year. We haven't done that yet, but it will come. So I hope you can read this. As far as the Hubble constant measurements, our best value is 75 plus or minus a rather large error bar. It doesn't solve Jeff Swiring's problem, but it does add to it a little bit. Adam Ries's value is over here in the middle with the small error bars of 73 point something, though there's a large number of values that hover around 70 something, and then there's the smaller number of values from the microwave background, and you've heard all about it. We don't quite know what causes it. I have some ideas, but let that be. There's another example. Other supernova went off in this particular cluster. I'll skip that for the sake of time, but that's a little higher redshift. We hope to get more epochs there, so we can also measure the Hubble constant in this one. I think you had this image in one of his background. This is the El Gordo cluster, which is the Spanish word for the fat one. This is the, like Laurel and Hardy, this is one of the more massive clusters, more than 10 to the 15 solar masses, a redshift 0.9. And so much so in 2 clumps, there's a clump here to the lower left and the upper right, that some of the background galaxies get stretched into pencils. They get basically spaghettified gravitationally. And that is like, that would be the thin one in Laurel and Hardy. And then there's this other highly unusual horseshoe, we call it the fish hook or Anzuelo, that is very highly stretched in the gravitational landscape from these 3 foreground white galaxies in the cluster. And when I gave this talk a year and a half ago to an audience like this, there was a fellow standing up, he was 93 years old. He said, "Roger, I knew Einstein personally. I was a kid in Princeton. I escaped the Holocaust." His name was Werner Salinger, and he had several encounters with Einstein in his office, and Einstein would play the violin for him. You can read that story at the bottom of this press release. And so, while Einstein never got to see these images, one of the kids that he knew got to see the image just fine. This is probably our best one. It made it to the New York Times over Christmas time. It's Christmas time in the cosmos, it said. It is another one of these monster clusters, 10 to the 15 solar masses. It's called MAX 0416, about 4 billion years in the past. And the beauty about this one is we observed it 4 times, so we could actually see individual stars go across these infinity lines. We call them the caustics, in 2 different papers. And you can see this in various stretched images, that single stars suddenly flare up by a factor of several thousand. And so we're now getting into the business where we're counting individual stars at cosmological distances, only because they're lucky enough to go across these infinity lines. I'll leave that one for as it is. This is probably our best case. This is called the Dragon, or the Dragon's Arc in Abell 370. The cluster is off to the north, not completely shown here. But in this highly lensed arc, there are no less than 46 individual stars going across the caustics, and therefore becoming incredibly bright for a couple of months. And that's how we see them. Let's see, I'm going to wrap up now. I'll finish with the last image I have here. This is an image of SPT 0615, a redshift 1 cluster, where I have to point it with my cursor. It's too hard to do with my finger. There is a little arclet here that consists of a number of globular cluster, protoglobular clusters at redshift 10.2 that are at that redshift only 50 million years old. So they formed at redshift 11 or so. And they are lensed behind this massive gravitational microwave background cluster. They found it with the South Pole telescope. Here's an enlargement. I want to leave this to you as my last chart. You can see how messy this universe is at a redshift 1. Everything collides with everything else. I'm so glad that we live in a rather isolated spiral over to the side like this one, but further away from this big mess, in a relatively quiet neighborhood. And I have a couple of verses to illustrate that. The Lord himself will establish a house for you. I will bring them back to this place and let them live in safety. Jeremiah 32 verse 37. And of course, Jeremiah 29 verse 11. I will not harm you, but have plans to give you a hope and a future. I think we should thank the Lord that we live in a very boring galaxy away from major galaxy mergers and supermassive black holes. Yeah? I have another chart on black holes, but I don't want to get into it. It's a bit technical one, unless you want me to talk about it. Actually, it's a cute chart. It's to the right. It vertically plots the black hole mass versus star mass. And for local galaxies in the red, it's a well-known established relationship. You get less than 1%, 0.1% of the galaxy's stellar mass ending up in black holes over here. But at the higher redshift, redshift 4 to 8, where the universe is only a billion and a half years old at most, the blue points are well above this line. As much as 10% of the galaxy mass is already in black holes, as you saw earlier in the things that Ross showed. And so we now think that over cosmic time, with lower redshift or increasing cosmic time at the top, black holes either grow slowly or rapidly, so that by redshift 7, they can have 10 to the 8 or 10 to the 9 solar masses. But they might have done so very rapidly, even more rapidly than the galaxy. So if you ask me who formed first, the chicken or the egg, it's the galaxy or the supermassive black hole. It's most definitively the egg, the supermassive black hole, formed before the galaxy. Or at least it started to form before the galaxy. So I'll leave you with this last thought. Have regard for your covenant, because haunts of violence fill the dark places of the land. Yeah, and we're so glad that we're not living close to a supermassive black hole like that. Here's my conclusions. I have said it all, so I'm not going to say it again. But from cosmic dust we were made, and to cosmic dust we shall return. And we're cosmic late bloomers, and that's a good thing. We live in a cosmic, quiet, and safe place. Thank you very much.